All right, two more reactions to go, and that will do it for this chapter. Both named reactions, yay. The first is the Michael reaction. And what Michael did was he said, okay, let's do our aldol reaction, but let's see what happens if we take the aldol reaction and ramp it up a little bit. Okay, so what if we have our enolate, we make a carbanion alpha to a carbonyl, an enolate, but instead of just another carbonyl, what if we add an alpha beta unsaturated carbonyl compound? Now this looks a little bit weird, but here is what we're going to make the enolate from. Note the pKa, we've got a carbon with two hydrogens in between two carbonyls, pKa 19 for these hydrogens. You add ethoxide, not 19, pKa of 9 for these two hydrogens. You add ethoxide, and you're going to snag one of these hydrogens off here to make this carbanion. And recall that the conjugate acid of ethoxide is ethanol, pKa of, about 16, which means ethoxide snagging one of these hydrogens, this equilibrium lies to the right, because these are pKa of 9. The conjugate acid, the product, is pKa of 19, a less strong acid. Chapter 2 taught us that this reaction lies to the right. So if we take this compound here and add ethoxide, we will only make this carbanion, a carbanion right here, this enolate, and that reaction will lie to the right. And the question is, what will get attacked? Recall when we're attacking alpha beta unsaturated carbonyl compounds, we can attack 1,2, we can attack the carbonyl compound, or we can attack 1,4, attack this beta carbonyl alpha beta, the beta to the carbonyl. And which way does it go? Well, we have a choice. A little review here. Recall with alpha beta unsaturated carbonyl compounds, if we had Grignards or alkyl lithiums, they always attack the carbonyl carbon. They always attack 1,2. Organocuprates, on the other hand, always attack 1,4, will attack that beta carbon. So the question is, which way do these enolates attack? They always attack 1,4. So this guy here will always attack the beta carbon of the alpha beta unsaturated carbonyl compound and form a bond right here. So note in the product, we form a bond here and the double bond goes away. Still have the carbonyl of our original alpha beta unsaturated carbonyl compound. We just get rid of the alpha beta unsaturated part and we attach this enolate to that beta carbon. And truthfully, I'm not going to worry if you know about the mechanism. Here it is right here, and it's exactly what you would expect. The end gets a little bit tricky, but yeah, we attack one of these hydrogens, make this carbanion, attacks beta, attacks 1,4. And then this double bond breaks to make a carbanion here, and it just gets protonated. That's all we do. Okay, so let's look at this. If you had this alpha beta unsaturated carbonyl compound and you had this beast right here, and you added hydroxide, note that we've got a hydrogen right here with a pKa of 9, so this becomes a carbanion. Michael reaction says a carbanion of an enolate, an alpha beta unsaturated carbonyl compound. This carbanion will attack 1,4, will attack this carbon, and realize carbonyl stays, double bond's no longer there, and this carbon is now attached to that ring. And this looks a little funky, but it'll look like this. Yeah, let's check it out. We've got all this part right here, carbonyl. We've got this is carbon right here is now CH2. Here's our beta carbon. It still has that. It still has this methyl on it right there. And is also bonded to this carbon, which still has its methyl on it, and these two carbonyls and the ring and everything like that. You need to get in the habit of whenever you do a Michael reaction, whenever you draw the product, it's a good idea. It's not necessary, but it's a good idea to draw this carbonyl on the left like this, this group coming off the carbonyl here, draw that coming down off the carbonyl, and this group connected to the other molecule that attacked, to our enolate that attacked, have it coming around like this. In essence, whenever you are done with a Michael reaction, because we almost always start with these enolates that have these dicarbonyl enolates, we almost always start there. We don't have to, but since we often start there, no matter what, we're going to end up with one of these carbonyls still intact, because this carbanion does the attacking. Nothing happens to either of these carbonyls. Heck, nothing happens to this carbonyl. So we'll always have this carbonyl and a carbonyl on the other molecule, the enolate, always intact. Get in habit of drawing them parallel to each other like this, so that they're running like this. And what you find, because this is our carbonyl compound, here's alpha, here's beta, and beta is always attached to a carbon alpha to another carbonyl. This is the bond right here that always gets formed. We will always have this kind of geometry. And it's a good idea to get in the habit of drawing it this way with the two carbonyls like that. First of all, I think this looks a little nicer than this over here. This looks like all spread out and whatnot. This looks a little nicer. But the reason for always drawing it this way is our next reaction, because what often happens is after our Michael reaction, which is an enolate with an alpha beta unsaturated carbonyl compound, we often get a Robinson annihilation. It's a Michael reaction followed by an intramolecular aldol reaction. Yeah, so here's the Cliff Notes version of it right here. If we have, alpha beta unsaturated carbonyl compound, if we have a molecule that can make an enolate, so if we add base here, we have this enolate right here, have a negative charge here, we will get this. We will get two rings bonded together and a double bond. We regenerate an alpha beta unsaturated carbonyl compound. But here's the deal. If we look at this the way it's drawn, and I always also recommend when you're doing a Michael reaction, since you're always going to have an alpha beta unsaturated carbonyl compound, always draw it on the left. To the right of it, draw our what's going to become the enolate, here our cyclohexanone. Line up these two carbonyls so they look like this, and put the carbon that's going to become the carbanion up like this. What we're going to see is when we make the product here, that this carbon-oxygen double bond is actually going to become this carbon-carbon double bond, with this carbon over here being this carbon of this double bond. So we're going to end up forming a double bond between the carbonyl of our enolate and the carbon alpha to the carbonyl in our alpha beta unsaturated carbonyl compound. And these guys tend to be pretty stable, so these reactions go. Alright, so let's look at the mechanism of this reaction. It's a little complicated here. But truthfully, it's not that bad. The only complicated part is keeping track of your molecules, keeping track of your carbons, and where everything is going to go, which is why I recommend drawing it in this fashion. So if we started with this alpha beta unsaturated carbonyl compound and this beast right here, we note up pKa of 9. Here are the protons that are going to get snagged to make this carbon a carbanion. All right. I strongly recommend drawing this with our carbanion here, double bond here. I didn't do it here. I should have. And I would have drawn this alpha beta unsaturated carbonyl compound right over here with a double bond here, single bond down, double bond to the oxygen over here. Because when you do that, you just take this beta carbon and form a single bond to this carbanion, because this carbanion is going to attack beta. It's a Michael reaction to form this bond right here. So the first Michael reaction, recall Michael, the enolate attacks the beta carbon, double bond is gone, this carbonyl stays, and this carbon is just bonded to the beta carbon, and this is what you have. This carbonyl is this one, this CH2, this becomes a CH2, this becomes a CH2 here and here, bonded to this carbon, the carbanion, which still has the methyl and those two carbonyls on there. And as I said before, draw this carbonyl parallel with that carbonyl, because what will happen with base, we still have base around, and now we've got, ooh, here's this carbon alpha to the carbonyl, pKa of 19 for these protons here. And so we can form an enolate with base, which then will attack this carbonyl carbon to make this beast right here. It'll form that ring. We can get some protonation, and now we've got, oh, OH here, H here. Recall a little deprotonation, just like our aldol reaction occurs, had deprotonation here, and we get that forms a double bond. All right, so this is a reaction that does occur, a Michael reaction followed by an intramolecular aldol reaction, and that does happen, we get this Robinson. And so note, we went from this beast here and one ring here to this beast here with two rings, and we still have an alpha beta unsaturated carbonyl compound. We have a ketone here, lots of functional groups that can be used for further synthesis. All right, and that ends chapter 24, I believe. That is the end of this chapter.